Okay, so for bonding, let me scroll this down a little bit. Whoops. So we're talking about chemical bonding today. Why, looking around you, why don't we see like different elements just by themselves? Okay, they bond. When elements by themselves bond, what do they make? Compounds. So everything, most of the atoms, elements, everything's made up of are unstable. Very few of them actually have their full valence electron level. So instead, they like to bond, which makes compounds. So what you see, water, is a compound of multiple elements. Okay? Oh, I should have just not answered that question. So why are they always forming compounds? What do they want to do? They want to stabilize. Change this. And how do stabilize? That is not how you spell that. There's no E, is there? It's just stabilize. I can't spell, guys. Okay. Your elements want to stabilize by doing what? What is bonding doing? When our elements bond, what are they coming together with? How do they stay together? They're sharing electrons. So all of our bonding things are going to be about electrons. That's why we talked so much about valence electrons last week. Excuse me. And all of these atoms are trying to get this octet rule. They want to have a full set of valence electrons. Usually this is 8, except what doesn't have 8. Both of those, hydrogen and helium. How many do they need to be full? They just need 2. So if they've got a full outer shell, an element is more stable. It's less likely to go off and be radioactive. So in order to get the full 8, our atoms will either lose electrons, gain electrons, or share them. And they do this whichever way works the fastest for them. So metals, how do you decide what is a metal? Where on the periodic table are metals? A bunch of them are in the middle chunk, or to the other way. To the left. What? Okay, so elements that are metals are to the left on the periodic table. So those are going to lose electrons. Remember there's the stair step, and then you remember by iron is on the left. Non-metals are going to gain electrons. Why is that? You could just read. What do you remember about elements on the right side of the periodic table? What? Depends. Their atomic number is their protons. Yep, their digit, the last digit of the column they're in is what? That number tells you what about the element or the atom? Nope, not mass. Yeah. The further over they have a fuller set of valence electrons. So since they have more protons, they have more electrons to match. The ones that have a full set are called noble gases. So that column 18, helium, neon, argon, krypton, xenon, radon, and I don't know how to say the last one, are noble gases because their valence electron shell is full. Agnus. Yeah, I don't know how to say that. It's fine. We're not going to use that one. Yeah. The electrons there are like they're set. They don't need to run away to be full. They're already full. What does that say? Don't feel. That's a typo. The electrons don't feel much attraction to the nucleus. Nonmetals have more protons, and then so they can attract more neutrons. So they're more positive. More protons means more positive charge. So the bigger the charge, the more they can attract. Okay? Any questions about telling the difference? We already talked a little bit about ions, right, last week? So this is just a little bit of review. Do you remember what an ion is? Okay, well, let's talk about it so you do. Yes. An ion has a charge. So usually, in general, we talk about these as just neutral atoms. The protons and the electrons match. For an ion, they don't. An ion has a different number of protons and electrons. Okay? To find the charge, you need to know how many of each they've got. And then we do protons minus electrons is the charge. We're going to either get a positive or a negative number, depends on what we've got. But you show something is an ion by writing the symbol, whatever your element is, and then the charge, and then after that you put if it's a positive charge or a negative charge. So here for magnesium, Mg is magnesium. It's got a positive 2, which means it had to lose 2 electrons. So it kind of feels backwards. Do you remember that? More specifically, last week we just talked about the charge. You can separate these by which one they are. A cation.
That just looks like caution.
It's like what?
Caution.
Caution. If that helps you remember it. Caution, these are positively charged. I don't know how to... Here's how I remember it. Cat and pause. What? Anions. Yuck. Negative. There you go. So cations are positively charged. They lose electrons. Anions, if you're Tyler, are negative. They've gained electrons. Caution onions. But how does that help you remember positive or negative?
Onions are going to make you cry.
Onions are make you cry, which is a negative feeling.
And 9 10 if anything is caution.
Great. If whatever helps you to remember, you put that in your brain.
Yes.
For me, cat and paws goes better than caution and positive things. I don't know.
Why would you need to be cautious or positive?
I don't know. That's why I said cats and paws make more sense to me.
Caution would be happy.
Caution is happy. Just whatever is in your brain, cool. Remember that cat ions are positive and anions are negative. Okay. So over here it says, give the ion notation for an atom that has 20 protons and 18 electrons. What do you do to decide the number? 20 minus 18 is a 2 positive. Whoops. Remember we do the... Oh, wait. The 2 positive is correct. But they want us to know, we need to know what the ion is. So how do you decide what element this is? Look at your periodic table. What's going to tell you what element this is? How do you know it's calcium? The number of protons. Its atomic number is 20. So what's our symbol? Ca, and then 2 plus as a superscript.
How did you do that last part?
Decide that it's calcium? So remember, every element is made up, like you decide what it is by the number of protons it has. So they're telling us there are 20 protons here. So go to your periodic table and find the number 20. And that's what element it is.
So the next one, just kidding.
The next one they gave us. But you still need to know, they're saying sulfur. What do you know about sulfur? It's got 16 protons. Sulfur's atomic number is 16.
And its thing is S.
Its symbol is S. What else do we need to do here?
16 minus 18.
We have 18 electrons. So 16 minus 18 is a negative 2. S2 negative. Questions there? Does that make sense? All right. Don't worry too much about this bottom question, but it says, what force will the ions feel? So we talked about all of our elements want what? What do these elements want? Want to be stable. They want their protons and their electrons to match. So there's a few different, I'm not exactly sure which word it is. We're just going to go with the electron force. Electromagnetic or electro something. We're just going to call it the electron. The rule that tells you when they're stable is called what? What is the rule that tells you if an electron is stable or not? The octet rule. So that's why. They want to have that 8 electron shell. Okay? All right, any questions about the top of this page? So if you look, here we're going to talk about how these, the different bonds we can make. So we've got different types of bonds. We're going to talk about ionic bonds right now. Ionic bonds are between metals and nonmetals. Okay? Oh, man. So by itself, if you just have sodium, excuse me, it says it's very reactive. It'll just explode if you put it in water. We are not doing that experiment. I am sorry for you.
Hey, what's that explode if it
Not doing it. Also, I don't like just have sodium by itself. It's not a very easy thing to, source. So, instead, what? No, thank you. So, instead, where is sodium? It's in the first row. It's just got this one valence electron here. That's what's making it unstable, that one electron. So to make it stable, we lose that electron. What row is sodium in? Okay, sorry. That's the first column, third row. All right, so the first column is why we got that one electron. The third row tells us what about sodium? Good. Because it's in the third row, we know it has 2 full rows before that. 2 full electron levels. So if I lose 1 electron, what's going to happen to my electron levels for sodium? Okay, so if I drew this like a Bohr model, like we did before, I'm going to do up here. No, because the protons are not changing. So remember when we did our Bohr models, sodium has 1 full for 2. 1, 2, 3, 4, 5, 6, 7, 8. 1 full one for 8. And then just normal sodium has 1 extra out here in the third. But if we got rid of this, if we lost this extra electron, yeah, we end up with a full shell here, which is stable. So the protons didn't change. It's still sodium. But if I lose 1 electron, what happens to it? Yeah, it stabilizes and... What'd you say? Okay. How many protons? This is 11. So if I have 11 protons, how many electrons do I have if I lost 1? 10. What does that mean about this sodium now? What? It has 10 electrons. Nope. If it's got 10 protons, then it's not sodium anymore. It still has 11. It still has 11 protons. So if we got 10 electrons, but 11 protons, what does that mean about my sodium? It's an ion. We just changed its charge. So now it's positive, positive, cat's got pause. It's a cation here. And losing these electrons is how the bonding happens. Okay, so that was sodium. We're also going to do this with chlorine. On its own, chlorine is a poisonous gas. But it's got 7 valence electrons, so it's not going to explode in water. It's just a little dangerous. Not a lot. But it does need one more electron to be stable. So if my, somewhere this chlorine finds 1 electron, had 7, to be full it needs 8. Yes? Oh, that's a typo. Yeah, they can both be cations. One is positive and one is negative. Yeah, so good that the creator of this just didn't change their thing. But now it's full. But how many protons does chlorine have? And it gained an electron, so now it has 8, which is how we got this anion.
Chlorine has
17, sorry. So then it would have 18. And that is a typo. Cross out cation, that's not right. It's an anion because it's negative. Anion. It is. Okay, so if you put these two things together, if sodium gives up its electron and chlorine takes it, this is a bond. They made a stable compound, and sodium chloride is what you eat in your food. It's just table salt. So that explosive sodium that would explode in water and this poisonous gas chlorine, if you put them together, they make something we eat every day. Table salt. It makes you know. It's stable. It's fine.
Yeah, until you make it unstable.
Well, don't make it unstable and we'll be fine. These ionic bonds happen besides just attracting. They had the same number but opposite, what's that called? Charges. So this bottom part is asking, will these make compounds? So you need to look at the number and the sign of the charge. So for magnesium 2 positive and lithium 1 positive. Are those opposites? No. They have, first of all, before they can you even need to look at the number, you have to decide, are they going to be attracted to each other? Does positive attract positive? Does not. So that's not going to happen. Calcium and fluorine?
Yes,
Okay.
but it'll be a positive one.
They will be attracted to each other. Have to work some things out, but yes. Next we got sodium 1 positive and oxygen 2 negative. Done. Those are opposite signs, right? Opposites attract. Oh, why not for the last one? They're both negative. They'll repel each other. Done. This next set are just giving you the elements and not their charges. So we need to decide some things about the charges. What do you know about potassium? Okay. How many valence electrons does it have?
Fourth row, so
Fourth row, which column?
first,
First column. So how many valence?
3 full rows.
Valence means the outer shell.
One.
1 valence electron.
So 3 full rows and 1. So to make that positive,
Let's look at lithium before we decide.
Lithium is 1, 4, and 1 on the outside. So 3 total.
Okay. Will these make ionic compounds? Also, what do you know about potassium and lithium? They don't mix. Where are they? What type of elements are they? They're both metals. And ionic compounds have to go between what? Metal and non-metal. So is this going to work? No. So if they're in that same column, not going to happen. Okay. I don't have the picture on the wall, but remember the line for the metals starts underneath boron and does like a stair step. So yes. What? Everything left up. So like aluminum, germanium, antimony, polonium, and tennessine are on that stair step line. When we're done with this, I'll pull it up again so you all can highlight the line. So why is this one no? Oh, I'm sorry. Why is that one yes?
Because it's going to aluminum, fluorine.
Okay, aluminum is a metal. Fluorine, not a metal. What about beryllium and what is that? Chlorine? Metal. Chlorine is not a metal. So those will work. Iron and oxygen. Iron is a metal, oxygen is not. It might rust, but they'll still bond first. Okay, I started to make that way too hard. Just metals and non-metals. Any questions there? Before we flip to the back page, I'm going to pull up the periodic table. Okay, so here's our periodic table. The line starts underneath boron. So it goes like this and just stair steps down. Everything to the left except hydrogen is ruined. But everything to the left of that line is considered a metal. Everything to the right, including hydrogen, are non-metals. Yeah, so that is like pulled out of the middle. They're special, but they're considered non-metal or metals. There are, well, it doesn't matter for us. These ones touching the red line are considered metalloids, but for this bonding stuff, just anything to the left is a metal, anything to the right is a non-metal. All right, so go ahead and turn to the back. The other type of bonding we're going to work with is called covalent. the way they've got this, like the memory device here, for covalent bonds, they cooperate. So for our ionic bonds, one electron was going to the other element. Here, they're actually going to share them. So if there are no opposites around, if we can't make an ionic bond, you can still get a full 8 by sharing your electrons. This is covalent. So when you're asked the difference between ionic and covalent, for ionic, opposites are attracting and they're giving electrons away. For covalent, they're just sharing them. Oh, my ears. Okay? This happens between nonmetals. All right, so if you look here, we have 2 chlorine atoms. The black ones are, chlorine is in what column? No, column. 17. So they have 7 valence electrons. So all of these black dots are the valence electrons, and then the white is an opening. So these both have 7 full spots and 1 open spot. And they're just going to share their little electrons here so that then they both have 2. They're sharing them, but they would both have 2 there. When you show this with just a straight line, one line means a single bond. Okay? Bless you. The difference for the number of bonds, if you look at oxygen, what column, how many valence electrons is oxygen? What column? Yeah, it's in the 16th column, so it has 6. So you see they've got 6 black dots there, which means they both have 2 open spots. So what they did is these 2 got shared with those 2. So since they needed 2 each, this is where that double bond came through. So you show 2 lines to show that they're sharing 2 electrons each. So let's do the dot diagram over here for nitrogen. What column is nitrogen in? 15, so how many valence electrons? 5. So I've got 1, 2. For these, I know we went like the zigzag way. For these, just do 1, 2, 3, 4, 5, just for time. It is a child. 1, 2, 3, 4, 5. So how many spots are open? 1, 2, 3. Yeah. So these both need 3. So to show that they need 3 each, you're going to draw 2 ends. And then how many lines in between them? 3. They need 3 each, so we're triple bonding here. Oh, goodbye. Oh. All right, so same idea for fluorine. Where's your mama?
Right behind her, I have a cable.
Okay. Goodbye. What row is fluorine in? Column. I keep saying row. What column is fluorine? 17, okay? So that'll be 7. How many spots are open on each fluorine? 1. So when you draw your bond, you've got your 2 Fs, and how many do they need? Just 1. They both have 1 open spot. Okay, does that make more sense how to decide? Whoops. All right. And the other part of this is deciding ionic or covalent. How do you decide which is which? Ionic works between what? Metals and nonmetal. Covalent. We just talked about at the very top. Is for 2 nonmetals. So the first one they gave us here is MgO. Yeah, what elements are those? Magnesium and oxygen. So what type of elements are they? How do you decide? Do you have your periodic table out? Find the Mg. Yeah. That's true, but we don't need to know that right now. I need to know what type of element they are.
Magnesium is an alkaline earth.
That one is way too specific. Remember, just use the line. Is it metal or non-metal? It's a metal. Oxygen is a non-metal, so this has to be ionic. P50. P stands for phosphorus. Is phosphorus metal or non-metal? Non-metal. Oxygen, non-metal. If they're both non-metal, what type of bond is it? Covalent. All right, CaO. Ca stands for calcium. Metal or non-metal? Metal. And oxygen is a non-metal, so ionic. All right, you guys go ahead on your own and do those other 3. And then we've got 2 more things to talk about on this page. Oops. All right, 2 more things. Next thing is oxidation numbers. So an oxidation number, oh, I cut it off. Let's go back up. So the charge that an atom gains when they lose or gain their valence electrons are the same thing as the electrons that they gain or lose when bonding. And that is the oxidation number. So basically we're just looking how many valence electrons do they have, because that's how many they'll give up. So first here we have Be for beryllium. Remember, valence electrons come from the column they're in. So beryllium is in the second column. Okay? What? Well, hold on. We got to decide positive or negative. So, why? The metals are more likely, that actually is right. Because it's on the farther to the left, it's going to lose its electrons. But when it loses them, what happens to its charge? Kind of does the opposite. So if they lose electrons, they're a positive charge. Feels backwards. Do you remember that part? Yeah. So like if they gain electrons, then they become negative. Yes. But if they lose electrons, then there's more protons, so now they're a positive charge. So it feels opposite of what it, like if they lose, let's write it up here. If they lose electrons, then they have more protons and are positive. If they gain electrons, then they have more electrons and they're negative. And that metal or non-metal is how you decide those. These are gaining or losing electrons. We'll just do this first row together. Oxygen for O. Oh, they gave you the oxidation numbers up. I am silly. You don't even really have to figure this out. They gave it to you. It would be in the 16th row. So it would have 6. But it's on the paper. If it has 6, how many does it need to get to 8? 2. And then is that going to be positive or negative? It's going to be negative. Okay? Chlorine. 17. So how many does it need to get there? Just 1. Is it going to be positive or negative? Negative because it's further to the right. N is for nitrogen. Okay, it's in the 15th row, so it needs 3. It's a non-metal, so it's negative. And then lithium. He's fine. So in the first row, or column, I keep saying row every time. It needs 7. But it's going to, instead of gaining 7, since it's on the left side, it's going to lose it instead of gaining. It's going to be what number? 1. And it'll be a plus. So it always wants to do what's easier. So like 1 is easier to lose than 7 is to gain. Does that part make sense? Okay. You are trying to get to 8, but if it gets rid of 1, then it does have 8 from the rows before it. So like the ones on this side are going to lose them because there's less to lose. It would take less work to lose 1 than it would take to gain 7. I'm sorry. How else can I say this? Does anybody else have a better way to explain? If you're watching the video, do the second column here on your own. Okay, let's finish this page. Well, we were going to start the other one, but we'll see. We'll see. All right, you can figure out how to make stable ionic compounds using the oxidation numbers. So those oxidation numbers are important when you're deciding if things can bond. So lithium 1 gives up 1 electron. Oxygen -2 needs 2 electrons. So those signs are very important. And these need to be even. So like there it says oxygen needs 2 lithiums to be balanced as a compound. And this is their process for showing how to decide how many you need. So you write the symbols. We've got lithium with its +1 and oxygen with its -2. And then they cross the numbers. So in order to match, we need 2 down here and 1 down here. So these big numbers are just your steps. So to be a compound, this bottom number tells you how many of the element you need. So we need 2 lithiums for every 1 oxygen. Okay? You don't have to keep the charges up top because once they're combined, they're neutral. Does that make sense though? Sure. They did another one here with calcium and oxygen. So that table up top helps. What is the oxidation number for calcium? They told you there. So in the second column, 2, and it's in the beginning, so it's going to be a positive. Oxygen is in the 16th row, so it needs 2, but it'll be negative. And then you're going to crisscross these, 2 and 2. But if they match, you can reduce the numbers. So think about it like a fraction. What is 2 over 2 going to be? 1. So you really just need 1 of each. Does that make sense? No. Think about this as 2 over 2. These bottom numbers, if they can reduce, you go ahead and reduce them. I have aluminum and chlorine. Oops. What's the oxidation number for aluminum? It's up here. What row is it in? Or column is it in? The 3. And if it's to the left of the line, it's 3 positive. And up until, what is that? 14? 14 and below are positive. So where carbon is, anything to the right of carbon will be a negative oxidation. All right, and then we have chlorine. Why isn't it writing? What's the oxidation number for chlorine? So 1 negative for chlorine. So we need to crisscross these. Can we reduce 1 and 3? No, they're not divisible. So I need 1 aluminum. If it's a 1, you don't have to write it. And 3 chlorine. So ACl3. Okay? What part is confusing? And then we've got sodium and sulfur. Yeah. Sodium is 1. Sulfur is 2. So crisscross your numbers. Do this the same direction. Na gets 2. Sulfur just gets 1, and you don't need to repeat the ones. So Na2S. Questions?